happens, and some amount of energy will be released in the process. If you throw a motor on that thing, you can get electrical work out of it. Throw a light bulb out there and get light to be generated. Okay, so now we're starting to get into that stuff I was talking about with phase boundaries. So my question for you is, we showed that if you connect those guys through a conductor, that the pull will be felt through the conductor and electrons will be stripped away. What happens in that solution if you don't provide the electrons an easy path to travel through? Talk about that right now. Essentially, if you don't provide the electrons an easy path for moving from one side of the solution to the other, from one phase to the other, from the place of high potential to the place of low potential, if you don't provide that, then the fields that exist between the phases will cause the matter itself to react in a way that tries to minimize whatever the applied potential is. So in these in the cells above, we had phases that were negative, like the hydrogen phase, because it had those electrons it was giving up to the silver electrode would be negative, and a phase that was positive. So the silver electrode would have been a positive phase with respect to that. And they were separated by a solution. And we connected them through a conductor, and electrons moved from the conductor from negative to positive. If you don't provide that conductor, what happens is in the solution, positively charged species will migrate towards whatever phase is negative, and negatively charged species, this is supposed to be an X minus, will migrate towards whatever phase is positive. So again, this doesn't have to be, I've drawn a capacitor dipped into a solution here. It doesn't have to be a capacitor. A capacitor is just an easy way to envision this. We're just talking about phases that have different magnitudes. One of the phases is positive, one of the phases is negative. So these ions will move, like we saw, and they'll try to essentially neutralize the potential that they feel by setting up a counter potential. You'll notice that on the capacitor, we've got positive charge and negative charge. That'll result in a field vector that points in one direction. In the solution, we've got negative charge over here and positive charge over here. This results in a field vector that points in the opposite direction. And the two field vectors together tend to cancel out the field, or the total field. They tend to minimize the total field. So the solution acts to try to push against the push that it's being pushed on with. We saw that when things conduct, if the potential is strong enough, that once these negative charges over here make it to the positive plate, the electrons will be removed, and you'll get some kind of chemical reaction here when those electrons when that oxidation happens. And then over here at the negative phase, the electrons will pop off onto the positive ion, and we'll get current. But that current only happens if the magnitude of the field strength is large enough to pull those electrons off. If it's not large enough, you'll get this kind of a situation here where one plate has positive charge on one side, negative on the other, and the other one has negative charge on one side or positive charge on the inverse. This is important. This is important. Let me go to the next image. You can read my notes later. I'm just going to talk for now. This is important because of the following. It turns out that the field strength, when the solution responds this way, weakens in the interior of the phases, but it attains a very, very large magnitude right at the phase boundaries. So we just said that at that phase boundary, you've got a bunch of positive charge, a bunch of negative charge lined right up next to each other, right? Kind of trying to draw that image here. So I've got positive charge on one side, negative charge on the other. I've drawn a bunch of lines. That's to indicate that there's a high field strength between those. Imagine that you're an electron, right? And you're moving from one side of this solution, or from one phase to the other. Now, I didn't draw this, but over here there's kind of positive charge on the other side. And the positive charge and the negative charge, their fields tend to, well, I shouldn't say that. Anyway, so right across this boundary, when you begin to move from one side to the other, and you're an electron, let's say you get to right here, just to the interior, you're going to feel a really, really, really large push from all of the other negative charge that is present on this boundary. You're going to feel a very, very large pull from all the positive charge that's sitting over there. Essentially, there's just a really, really large magnitude electric field sitting in between those two spaces. And so as you move across, if you're an electron and you're being accelerated by that field, then you're going to a lower potential energy, right? Your electric potential energy is being converted into kinetic energy or energy of some other kind, depending on how you harvest it. And so as that electron moves across, the value of its electrical potential changes by very large amounts. Similarly, it goes to a lower potential, it releases electric energy. Similarly, if you take a positive charge and you cross that, if you try to cross that boundary, you're going to be being pulled back by the negative charge on this side, and you're going to be being repelled by the positive charge on this side, and so you would have to put energy into a positive charge to make it cross that boundary. The point is that across a solution, or across a cell, an electrochemical cell, the boundaries between the phases are areas where there's very, very, very high field strength. And so the electrical potential changes by large magnitudes as you cross from one phase to another. Let's go.
Sorry, just to be clear, this is the phase boundary like you were talking about before, where the charges just separate, right?
Yeah, let's go back to another image, and I'll use that other image to try to point this out. So, looking back at this image that we had, we said that the zinc was, this is going to be our negative electrode because relative to the silver over here, it's at a negative potential, right? The silver's at a high positive potential. So the zinc is the thing that you can envision having that excess of negative charge on it, right? That excess of negative charge, if you don't allow current to flow, will cause ions in this solution, positive ions, to move towards it. And so you'll have an excess of negative charge here, an excess of positive charge here. And so as you cross from the metal to the solution, you'll cross a phase boundary, and therefore your electric potential will change as you cross that phase boundary. Similarly, this electrolyte is in contact with the silver chloride. And so there'll be similar effects between the electrolyte and the silver chloride. So as you cross from the electrolyte over to silver chloride, you'll be crossing one of those phase boundaries where there's high magnitude fields. And so your potential will change as you move across that boundary. Then you got the silver chloride solid in contact with the silver. Again, there's going to be some difference in potential, And so there'll be a phase boundary, and there'll be some separation of charge across it. And you'll, if you're an electron, as you move across that separation, you change your electric potential. So in all, if you want to figure out what the total change of potential is across that cell, you sum the potential or the effects on your energy based on crossing all of those boundaries. If we wanted to figure out what the total change in potential was across this cell, we'd have to figure out what the change in potential is when we cross from the solid zinc to the solution, when we cross from the solution to the salt, the solid salt, and from the solid salt to the silver ion, right? Or the solid silver. It's those phase boundaries that create the changes in the potential of the cell. This is why they use that double line, that double vertical line. If there's a boundary between two phases where you don't really need to be concerned with the change of potential as you move from one phase to another, they'll stick that double vertical line in there to tell you, to remind you that, yes, this is a phase boundary, but it's not one that's very relevant to anything because the change of potential across is essentially zero. When you connect two ionic solutions via a salt bridge, you keep the chemical potentials of the two ionic solutions relatively equal. And so you can actually neglect the phase potential moving from one ionic solution to another as you cross that cell. So oftentimes in cell notation, you'll see a double line between two ionic solutions that are connected by a salt bridge. If they're not connected by a salt bridge, you might not see a double vertical line. Okay, so So, just a reminder of what happens in these cells in the real life and why we like to have salt bridges. Going back to that same cell that we were using earlier, if we don't connect these two, well, first of all, in this particular arrangement, you don't even need to keep these guys in separate containers because the solution's the same. You could just have them sit in the same solution, the electrodes sit in the same solution and run the experiment. That was the cell that we looked at previously. But assuming that we separate them and you let the thing flow, electrons move this way, you get a bunch of positive charge that builds up in this one, over here. The electrons get donated to the silver ions here, and so a bunch of negative charge shows up in this solution. And so what ends up happening is you get an excess of positive charge built up over here, and an excess of negative charge built up over here. That establishes a potential in the reverse direction. If you've got an excess of negative charge in this solution, that excess negative charge is going to begin repelling electrons that previously were trying to cross this bridge, right? And so there'll be potentials between the solutions, or the potentials of the solutions will change, the aqueous phases will change, such that eventually the electromotive force is turned to zero and no more electricity flows. So to prevent this, we provide a salt bridge. A salt bridge essentially allows the appropriate ions to travel into the appropriate compartment to keep this potential from being established, to keep that counter, the reverse potential, from being established. I'm really hoping I was going to have more time to get through these. All right, so into some thermodynamics. There's a derivation you guys should read. I don't think I noted it here yet. Section 4.13. So this goes, it uses a bunch of those partial differential equations that we used early on in the course. And it's derived, and the derivation 4.13 leads you to this equation. What this equation is saying is that for constant temperature and pressure, delta G ends up being equal to the amount of work other than pressure volume work, PV work, that you can get out of a chemical reaction. And the derivations, it's quick. You can go take a look at it in the book. But essentially, for a reaction that happens at constant temperature and pressure, the maximum amount of work that you can get out of the reaction is equal to delta G. So let's look at this reaction that we looked at early in the lecture. We said that if we just take the silver chloride and the solid zinc and we throw them in a solution together, that negative 233 kilojoules, so 233 kilojoules of heat is going to be released, all right? And so delta H for that reaction is negative 233 kilojoules. If you don't mix them this way, and instead you run it in a different setting, you take your electrodes, you dip them into a solution, and you put a conducting wire across it that runs through a resistor. And you dip that resistor into a calorimeter. So this is a calorimeter and this is a calorimeter. We're measuring the changes in temperature that happen here as the reaction takes place. You make this resistance infinite. You drive something up to infinite resistance, it makes the reaction occur reversibly. And you discharge this cell. You'll notice that as the resistance of this resistor goes to infinity, the amount of heat that you measure in this calorimeter approaches negative 190 kilojoules. So about 190 kilojoules of energy is being released into this body. And delta H down here ends up being negative 43 kilojoules, moving towards negative 43 kilojoules. You'll note that the sum of those two reactions, or sorry, the sum of those two delta H's is what we got when we simply mixed the two components together without separating them by that conducting bridge, right? The energy that was dissipated in this resistor did not have to be dissipated as heat. The resistor happens to turn electrical energy into heat, and so it manifested itself as heat. If instead we ran it through a motor, we could have turned that energy into electrical work in the motor or some other kind of energy. The take-home message here is that this energy is the maximum amount of work that we can get from this process. It was the maximum amount of heat that we could get to discharge the resistor. If it was negative 190 kilojoules, if it was a motor, that would have been the magnitude of the energy that we could, or the work that we could have gotten out of the motor. The heat that was released here was heat that went into entropy changes in that solution. That negative 43 kilojoules, if we write out our delta G equation, we know that delta H total for this reaction is negative 233. Negative 233. That heat, that entropic heat, negative 43 kilojoules, is equivalent to T delta S. Right, delta S is Q over T, and multiply T delta S, that's Q. And so this term represents those that entropic change for the reaction. And you'll notice that the sum of the enthalpy change and the entropy change ends up being that delta G value that we looked at when we said this is the amount of work that could be potentially done from the reaction or harvested from the reaction. one can you see better?
That one.
This one?
Yep.
Really wish I had better cameras. So, we just decided that the change in the free energy, the change in the Gibbs energy, was equal to the amount of work that we could get out of that reaction, right? The amount of energy that's released by that reaction. If you took that amount of work and tried to quantify it in terms of the cell potential, the potential across the cell, it would be equal to negative VFE, right? That's what we started off with at the beginning of the lecture. We said the change in the electric field energy was negative V times Faraday's constant times the magnitude of the field potential. And so we have the equation that delta G is negative VFE. This automatically makes us start thinking about the different manipulations that we've been doing with delta G. We know that delta G naught, or delta G at some non-standard state is delta G naught plus RT line Q. So we can plug that equation in and set it equal to negative VF times the E of the cell. Dividing through by EF, we get this term up here. The E cell is negative delta G naught over VF plus RT over VF natural log of Q. And we just define negative delta G naught over VF as E naught of the cell. And so now we have this equation that says that the E of the cell is E naught of the cell minus RT line Q. That's known as the Nernst equation. It just comes from setting the delta G equal to negative VFE and applying our delta G manipulations. And so we have an equation that relates the cell potential to the delta G of the reaction. The question is, how do we measure the cell potentials? And this is where it gets a little tricky. The same way that we had to for enthalpy changes, or for standard molar enthalpies and Gibbs free energies, etc., we had to establish some kind of a reference state. We have to do the same thing for electrochemical cells. And essentially it's because you can't measure a half cell potential, or the potential of a half cell by itself. Half cells are these guys that you're familiar with, Ag going to plus electrons forming solid silver, and zinc plus electrons moving on to form zinc. It's difficult to measure those energy changes because you have to have another electrode to hold the electrons over to. You have to measure the potential between the two electrodes. And so you can never just measure one half cell potential at a time. So what they've done is they've taken that platinum hydrogen electrode that we showed earlier, and they defined it as a standard. They said, we're going to use this electrode, and we're going to say that its cell potential is 0. And one of the reasons they do this is because the way that we saw that, well, anyway, it's easy to control the activity of this. So this electrode stays at a relatively stable potential, and because it does that, it's amenable to being used as a standard. So what they do is they take all of these half cells, like a silver ion half cell or a zinc ion half cell, and they hook it into that hydrogen half cell, and they measure the potential across it. And once they found out what that potential is, they assign that potential to whatever half cell they were testing against. So if you take a silver guy and you put it next to a hydrogen electrode, you're going to find that the potential across that cell is 0.223 volts, right? And that 0.223 volts is really the combination of the potential of the hydrogen cell and the silver cell, but we're just going to assign that value to the silver half reaction. So you run through, you make your tables, you test all of these guys against some reference cell, usually hydrogen, and you write out a series of E naughts. And you guys know what to do from there, right? In Gen Chem, you take E naught for a reaction, and for whatever redox process you are running through, you figure out which species is going to be oxidized, which is going to be reduced. You reverse the direction of the guy that's going to be oxidized. So in this case, if we had zinc and silver, we know that the silver is going to be reduced, and so it's written in the correct direction. The zinc is not going to be reduced. It's actually going to be giving up its electrons. So we'll flip that guy over, and we'll sum the two equations. We sum the two equations, you end up having to multiply by a coefficient, and you add these two cell potentials together, and you get something like 0.9 or something like that. I forget how much it is. You know, whatever that cell potential is. You're always looking for, because there's that negative coefficient in front of the delta G, you're always looking for the sum of the half cell potentials to be positive. If the sum of the half cell potentials are positive after you flipped one of the half cells and added them up, then you'll know that that positive cell potential will be multiplied by a negative sign, giving you a negative delta G, and so that is the spontaneous direction of the reaction. I really wish time wasn't running out. I just want to say one other thing. So we didn't mention, and you guys all know this, that simply by applying an external source, an external power source, you can force reactions to move in their non-spontaneous direction. Adding the half cells tells you what the spontaneous direction is, but applying an external power supply or voltage source to a value that's equal to the cell potential, equal and opposite to the cell potential, plus a differential amount over, will drive the reaction in the reverse direction. Okay, so I'm gonna put a homework together. We'll finish this up on Thursday. I'm gonna put a homework together and ship it out to you tonight. I think that this is the last homework that I'm gonna collect. We're gonna do chapters 10 and 11, but I don't think I'm gonna collect homework on 10 and 11. So this will be your last homework. But you are going to be tested on 10 and 11, so don't neglect those problems.
Is there another homework assignment you already gave us?